of this course, okay? And we will have our final exam next Saturday, okay? So I still need to record. Okay, yesterday we have talked about the principle of work and kinetic energy. The kinetic energy, to calculate the kinetic energy is actually, we need more knowledge about kinematics. We need to know its motion, its translation, its pure translation, pure rotation, or general plane motion, okay? And for the critical energy, which, yes, any problem? Yeah, the final exam will be on chapter 13 to 15 and 17 to 18. Yes, you're right. And also, we today we will talk about uh, just like linear momentum and angular momentum. So we'll including, we also include something of chapter 19, okay? So not only 18, also chapter 19, okay? So be back to kinetic energy. T equal to, yeah, let's talk about the exam next time, okay? So I will tell you the exact date and okay, on WeChat, okay. So let's just our class. Focus on our class, okay, because I need to finish the context today. For the critical energy, sorry, I don't know what's wrong here. Okay, let's just wait a minute, okay. There's something wrong about the pen. Need to recollect. Okay, now it's good. I would like to review the principle of work and energy because it's very, very important. So for the kinetic energy, and we will have two parts for the rotation, right? MVG, translation with the mass center and rotation about the mass center, okay? So for the pure rotation, it will be only for the kinetic energy of pure rotation. For the for the pure translation, okay, only this part. And for the pure rotation, it will be this mass moment inertia is actually the moment inertia about the rotation center. And sure, you can use this formula. I mean, you can calculate the kinetic energy for pure rotation, still translation with the mass center and rotation with the mass center. They actually equal to the rotation energy about the rotation center. And definitely for rigid body, which is doing general promotion, we should include its kinetic energy translating with the mass center and rotating about the mass center. And to apply the principle of work and energy, we need to calculate the kinetic energy of the rigid body system at initial and final position or initial and final moments. And also we need to calculate the work by all the forces. I mean, not only the force, but also the couples, right? So then we have the principle of work energy, the initial kinetic energy, plus the work by all the forces here and the couples. I mean, the external force system equal to the final kinetic energy of the system. Okay, and because kinetic energy is actually a scalar, the work is also a scalar. So it's a scalar equation and one equation, one unknown. We have just solve a lot of problems using the principle of work and energy. Today, we will continue study the conservation of energy. Actually, this part is a little bit similar with what we have learned for particle. For mass particle, we also have learned the conservative principle of energy. We know only if all the forces, we mean the work done by the force, only the conservative force do work to the system, so the collective energy plus the potential energy of the system will be constant. So it will be same. Actually, if you can solve the problem with the principle of conservative energy equation, you can also apply the principle of work and collect energy. So just sometimes if we apply the conservation of energy will be simpler, but it's the same actually. Just like here, because we know still the conservative forces, here we only still talk about the weight and the spring forces. So the weight and the spring force, they are conservative forces because the work by the weight or the spring force. Here, the spring force, we only talk about the linear spring force. The work done by the weight or by the spring force is not dependent on its path, right? Just like the weight, the work by the weight only depend on the position change of its gravity center, okay? So they are conservative forces. So accordingly, we will have the kinetic energy plus the potential energy will be constant. So the ratio we call them mechanical energy will equal to the final mechanical energy. But actually here, sorry, from this equation here, you see, we can say if we write down like this, sorry. Oh, sorry. I don't know what's wrong. We write down like this. T1, the initial kinetic energy plus the work done by all the conservative forces will equal to the final kinetic energy. This is the principle of work and energy, right? So actually, no difference, okay? So here, how to calculate the potential energy for the weight, just like the gravitational potential energy, is exactly same with what we have learned for a particle. The the potential energy for gravity force is equal to the weight times yg. What's yg? What's yg here? Yg actually is, you first need to define the datum line, and then yg is a perpendicular distance to the datum line. So yg may be positive or may be negative. That means the potential energy may be positive or negative, okay? So exactly like what we have learned before. So except for the gravitational force, also the spring forces are conservative forces. And for the spring force, its potential energy is calculated by the equation is equal to 1/2 K is actually the coefficient, and S again here, S is the stretchness referred to the unsteady position of springs. Here, S is very important, okay? S should be measured from the unstretched position of spring, okay? And the elastic potential energy will be always positive, okay? No matter it's compressed or it's put, it will be always positive potential energy. Why? Because the S, when measured from the stretched length, S is always larger than zero, or S squared is always larger than zero, right? So sorry, S can be right. So for the spring force, its potential energy should be always positive. And then if we need to apply the conservation energy law, and just like the before, we also need to draw FBD. Why? Because we need to know which forces will do work to have done work to the system, and if the only weight and spring force did work to the system, that means the energy should be conserved. We can apply the conservation of energy, right? And so we need to draw two diagrams. One with the body located at its initial position. Then we draw two diagrams to calculate its energy, the kinetic energy plus the potential energy, okay? And also we need to compute the kinetic energy of the rigid body. To calculate the kinetic energy, still we need to know they will have two components, translational kinetic energy and rotational kinetic energy, okay? And then we can apply the conservation of energy equation. So we just figure out it with more examples here. First, here the rod AB has a mass of 10 kg. Piston B is attached to a spring of constant K is given. The spring is outstretched when theta equal to 0. Neglect the mass of the pieces, and we need to find the angular velocity of rod AB at theta equal to 0 if the rod is released from rest when theta equal to 30 degree. Okay, so here the initial position of the piston is corresponding to theta equal to 30 degree, and then it is released, and we need to find the angular velocity. We need to find the angular velocity of rod AB. Here we have the initial position and the final position. And as I have said again and again, for this problem, generally we need to apply the principle of work and energy. Here, first we draw FBD for the rod AB, because here we neglect the mass, okay, of the pistons. So for piston A, piston B, there will be no, we don't need to consider them, right? Okay, so for AB, it will have the weight. And then for the pin, it will have the force, right? And for P, it will have forces. Oh, sorry. For B, there will be spring force, because we include B to draw FBD. And then we know that for the AB, only the rate and the spring force did work to rod AB. Am I right? After you draw FBD, first you need to draw FBD, right? For rod AB, after you draw it's very important for the problem of kinematics or kinetics, for the problem of kinetics, you need to draw FBD, because only after you have the FBD, you know just like here, which forces will do work to the during its motion. Okay, just sorry. Wait a minute. So for AB, we'll have the weight and the spring force, right? The weight and the spring force. Anything else? If we include A, we'll have the normal force, right? And the friction force, no, it is not, there's no friction force here, okay? And so when the AB at its initial position to its final position is here, becomes horizontal. And only the weight and the spring force do work. So actually, they are all conservative, they are both conservative forces. The mechanical energy is conserved for what AB. So we just have the initial position and the final position to draw 2FBD. For the potential energy, first to calculate the potential energy of the weight, you need to find the datum line, right? So we just establish the datum line in the line with the rod when theta equal to 0 degree. This is the datum line when it's horizontal. So accordingly, at position or at the final position, the potential energy will be 0. And except for the potential energy, we also need to calculate the elastic potential energy of the spring force, right? And here, the problem stated that the spring is unstretched when theta equal to 0. So since it's easy that when it's horizontal, the spring is unstretched, so its elastic energy, potential energy also equal to 0. That means at the final position, the potential energy and elastic potential energy should be 0. But except the potential energy, we need to calculate also the kinetic energy, right? Just for example, for the final position. For the final position, we need to calculate the kinetic energy of mod AB. What will be? So AB is doing what? General plane motion, right? T1 will equal to T1, T will equal to Vg plus Ig omega squared, right? And omega is actually what we need to find out. And how about Vg? Vg is unknown here, so we need to relate Vg and omega, right? Vg, how to relate Vg and omega? Here, A, we know it's velocity for B, right? Remember what we call what we have learned for the general plane motion. And we can find out, because for the A, we know its direction of velocity is horizontal, for B is vertical, and then we can draw the perpendicular line, right? Draw the perpendicular line to find its IC. Where is IC for what AB at the final position? A is actually the IC, right? Because velocity VA is to the right, and VB is to up, and we draw perpendicular line, and the intersection of the two perpendicular line intersect at A. So A is actually the IC. Okay, A is actually the IC. And so since A is IC, we know that VG should be perpendicular to the radius to the IC and equal to the radius times omega, right? So for the final position, we can express its kinetic energy in terms of the angular velocity. So this is for the final position. How about the initial position? Initial position, because at initial position, the rod AB is at rest, so its kinetic energy is equal to 0, right? T1 equal to 0. How about its potential energy? For its potential energy, first, the gravitational potential energy. The potential energy, according to what we have learned, is equal to W times YG. YG is measured from the datum line. Here, YG is below the datum line, so YG is minus. That's here we have the minus, okay? This is gravitational potential energy. And elastic potential energy will be always positive, and it's equal to here, this K is coefficient, spring coefficient is given, and this is the stretch length referred to is outstretched. The distance referred to the outstretched length. So this is S1, right? So we calculate S1, so we find out the total potential energy. The total potential energy is equal to the gravitational potential energy plus elastic potential energy. Okay, so for the potential energy and also for the kinetic energy. Kinetic energy, again, because the rod is released from from position 1, so kinetic energy at the initial position is equal to 1, okay? Here, this is what we have learned, right? We have done. So again, IC. How can we decide the IC of what AB when here? Because for A, its velocity should be horizontal, go to the right, and for B should be to the up, because piston A and piston B, they both are restricted to the channel, right? So the motion plane, piston A, piston B, they are translational, right? And so we can draw the perpendicular line of VA and VB, and the perpendicular intersect at A. So A is the IC. Oh, sorry, the VG should go up. Okay. And then we have the VG here. We have VG equal to R omega. R is equal to 0.2. And then this is the kinetic energy for what AB at final position, translation with the mass center, rotation about mass center. And here we use the relation between Vg and angular velocity, the final kinetic energy expressed in terms of the angular velocity. And then apply the conservation of energy, we can find out the angular velocity of the rod AB. Actually, here you see, definitely you can use the principle of work and energy. Sorry, I forgot to record. Okay. T1 of the rod AB plus, sorry, T1 plus rod AB plus the work by all the forces to will equal to the final kinetic energy. And here we know the work, only the weight and the spring force will have done work to the rod AB. So you can calculate the work done by the weight and by the spring force, you will have the same results. Okay, so that's why I said if a problem you can use the conservation of energy to solve, you can also use the principle of work and energy. Okay, and here the point is to judge to justify that only the conservative forces here, weight and spring force did work. And also one more thing is to calculate the kinetic energy. Okay. So here we only consider here the problem here said we neglect the mass of the pistons. The mass of the pistons. But if we need to include the mass of the pistons, for example, the piston is also 10 kg. Piston A, piston B, how to calculate this? How to find out the angular velocity of what AB? What will be different from right now? Here still involve two positions. So we still apply work and energy, right? We still apply work and energy, principle of work and energy. And or you still can use conservation of energy, because if we draw FBD again, just like here, we have piston A, piston B, rod AB as a system here. Definitely, we just don't consider the friction force. Okay, there will be no friction force involved, because if there is friction force involved, friction force will do work. Okay, so no friction force. Okay, so again for piston A, piston B plus rod AB, only weight and the spring force will do work during its motion. Okay, not only rod AB, the weight of rod AB will do work. Also for piston B, it's very important here. So maybe just like this, we still apply conservation of energy. So the first thing is to calculate the potential energy. For calculating the potential energy, here, the gravitational potential energy and the elastic potential energy at the piston 2 still equal to 0. Why? Because for AB, the gravitational energy, potential energy equal to 0, because this is datum line, right? And for piston A, the gravitational potential energy equal to 0. Here equal to 0, and the spring force is unstretched, so the elastic potential energy also equal to 0. So nothing changed. Even we need to consider the mass of piston A and piston B. Okay. However, at the initial position, the potential gravitational potential energy will need to include the gravitational potential energy of piston B. For piston A, again, its gravity center is in line with datum line. So here, gravitational potential energy should plus. This is its gravity force, its weight, right? And times. And also it should be negative potential kinetic energy, right? This is the distance to the datum line, okay? And elastic potential energy are same, right? Here, okay? So this is to calculate the potential energy if we need to include piston A and piston B, because here piston A, piston B, they are also have mass equal to 10 kg. How about the kinetic energy? For the kinetic energy, again, at the position 1, the T1 of the system is still equal to 0 because they start at rest, okay? But for the final position, the kinetic energy should include the kinetic energy of piston A and piston B, right? Here, it's very, very important. At the final position, the kinetic energy should include MA, VA, because A and B, they both are doing translation. That's right. And how about VA? How about VB? How to calculate the VA and VB? Here at the position 2, VA is equal to what? VA equal to 0. How about the VB? VB equal to 0.4 times omega 2. Why? Why VA equal to 0, VB equal to 0.4 omega 2? Because you see here, PA have the same velocity with piston A, right? Because piston A is actually doing translation. So the velocity of piston A is actually the velocity of a pin, right? So as we have say, A is actually the IC of what AB. So VA at this moment when theta equal to 0, VA equal to 0, VB equal to 0.4. 0.4 is the radius to IC, right? Is the distance to IC. And omega 2 is angular velocity. And so you can still find out the angular velocity, okay? So we continue to do this, okay? So if we need to find out, think about it. When theta equal to 0, when theta or the final position, at the final position, it's possible to find out the angular acceleration of what AB or the acceleration of piston B. Is it possible? We know for an instant, if we need to find the angular acceleration or the acceleration, we need to apply equations of motions, right? We need to apply equations of motions. What will be? So you can just draw FBD of piston B. If you draw FBD of piston B, what will be is the spring force and rate, and the force by A, right? We don't know. X component, Y component, and AB should be vertical, right? Spring force is given, weight is given, AB we don't know, and this force we don't know. Or you can just analyze AB, right? If we analyze AB and then weight XB, YB, oh sorry, here, this is XB, YB, and so the XB prime should be this one, YB prime, right? Action and reaction forces. And A, XA, YA, right? And then you can use what we have said, Ig alpha. You can just, this is FBD, and we have KD for what AB, right? For KD, it will have MA, AG, should have MAG X, MAGY. It's quite complicated. Okay, I just gave up. And then IG alpha, sorry, IG alpha. And then we can find out, okay, we can write down equations of motions, but if you need to know how to solve them, okay, I'll do this. The weight of the disk is 30 pounds and its kg equals 0.8. The spring has a stiffness of 2 pounds per feet and a stretchiness of 1 feet. We need to find the velocity, and the instant g moves 3 feet to the left. The disk is released from rest in the position shown and rolls without slipping. Okay, we need to find the velocity. At the instant g moves 3 feet to the left, okay, it already, so the spring has a stiffness is given and a straightness is also given, okay. We need to find out, just like this is initial position, and then this is the final position. And we draw FBD for this disk. We know that only the weight and the spring force and normal force and friction force. Even there will be some friction force, but it doesn't matter because it's without slipping. So friction force do no work. So during its motion, only the spring force did work to the disk, right? So we can apply conservation of energy, right? Sure, you can still apply principle of work and energy, okay? So it's a problem. And then the first thing, we need to calculate the potential energy, and then this is its initial position, this is initial position, and its final position. And because there are no changes in the gravitational potential energy, because the disk is moving horizontally, right? The gravity center, no change in its of the gravity. The gravity center change, I mean, the horizontally change, but vertically the gravity center remained unchanged. Okay, so only potential energy, we only need to calculate the elastic potential energy. At position 1, this will be the its elastic potential energy. Again and again, we need to know this. S1 is actually measured from the straightness, okay, is given, okay. And V1 is given, and similarly, we can calculate the elastic potential energy at position 2, okay. Yes, because here, the straightness is given, is 1 feet. So 4 minus 1 is equal to 3. We need to know this, okay? And here, because it's 3 feet, and this is 3, this is 4, so this is where should be 5. And then 5 minus 1 equal to 4 feet, okay? So that's why here, okay? So we calculate the elastic potential energy at position 1 and position 2, okay? Not only the potential energy, also the kinetic energy. the kinetic energy for the disk. Because again, just like here, the disk is released from rest. So T1 equal to 0, right? So for us, it's simple. T1 equal to 0. How about T2? T2, because disk is doing general motion, so its kinetic energy will include two parts, right? Translational kinetic energy, rotational kinetic energy. Again, we need to relate Vg and omega 2, right? We need to relate the velocity of the mass center with the angular velocity. Yeah, it's rolling without sleeping. So this will be the IC, contact point will be the IC. So it's very easy. We have the Vg is equal to the radius of the disk times angular velocity. So the kinetic energy can be expressed in terms of the angular velocity, right? So here we have the energy is conserved. So T1 plus V1 equal to T2 equal to V2. Okay, so we can find the angular velocity. So here you can apply the principle of work and energy, and no problem, you will have the same result. So for this one, I'm very, very interested that I would like you to find out. I would like you to find out the friction force. Okay, I would like you to find out the friction force when the disk moves to its final position. Okay, the disk is released in the position, and also we need to find out is the friction force and the AG, the acceleration of the mass center and its angular acceleration, and the friction force. So, how to do this? For this disk, we need to draw FBD, right? FBD weight and normal force and friction force. The friction force F and the spring force, right? Anything else? No, right? So we will have, this is FBD. We also have KD. KD, we should have MAG, right? IG alpha, right? And so equation of motion, so we will have F equal to MAG F equal to MAG, right? And all we will have, we find out the moment about the mass center. We will have RFR equal to IG alpha, right? Because if we calculate the moment about here and only the friction force will have the moment about mass center. And this one, we found that AG is actually equal to R alpha. Why? Why AG is equal to R alpha? Because VG equal to R omega, right? G moving horizontal. So take the time derivative, we will have AG equal to R alpha. So this one, actually, they are equal with each other. So there is no way to find out the force, the friction force, and find AG here. if we apply equation of motions. Right? Can we find out the friction forces? Can we find out the age here? No, we can't find this. Okay. So how about if we take the moment about IC, if we take a moment about IC, only MAG will have the moment about IC. Yes, try to take a moment about IC. You will find out AG, okay? Right? We also have equation of motions. We have this equation of motions. We can take the moment about the mass center from the AC is from FBD, the moment of the real force system equal to sigma mk G, right? This is from KD, right? And or we can just find any point. We can find any point, right? So you can try to figure out, okay, apply equations of motions, okay? Maybe we can just take 10 minutes break and then continue, okay?